This is video number 2 for the polyester family. So jumping right back into the applications of PET. PET is widely used in synthetic fiber production. If you have something that is made of polyester, it's usually made from PET. Fiber production is made by melt extrusion with a spinneret type die. It is usually quenched by shock cooling in air. Then the filament itself is annealed under tension to enhance the crystallization of the PET fiber. PET fiber, you want that to be highly crystalline. The melting temperature of that is typically 271 degrees Celsius, and it has relatively high moisture absorptivity. In making PET films, this is usually through the quenching of extruded sheets. It's extruded through a slot die, which this quenching just kind of destroys and disrupts the crystallinity. If you want it to remain as something that is clear, at that point you stop. If you want to take that amorphous sheet, you can heat it up to 80 to 100 degrees Celsius and anneal it with biaxial stretching. If you anneal it under tension at 180 to 210, you can enhance the dimensional stability and reduce the shrinkability of the sheet itself. Polyester is used in a lot of different parts. This is one example. This is DuPont's Rhinite polyester, and this is used in electric servo motors. These are the servo motors that deliver power for the Segway. Shown here we have America's Finest on Segway. PET resin is also used in electronic component encapsulation. Here we have example A is a wheel speed sensor for an anti-lock braking system, and this is encapsulated in the Rhinite 530 PET resin. Also, we have a gas discharge choke transformer, which is also encapsulated in the Rhinite 935 PET resin, shown down here. When parts are encapsulated with the thermoplastic, they come out of the mold ready to assemble. They don't require trimming operations associated with thermosets, and so this is, if you have a resin that's appropriate for encapsulation and has the appropriate properties, this is advantageous to be used in a thermoplastic process. Shown here we have BASF's Petra thermoplastic polyester. This is a gas assist injection molded PET. Most modern oven handles are made from PET. The Petra is a high strength, good stain resistance, excellent surface appearance, and it replaces a traditionally painted metal handle in the oven. When I was pregnant, I would routinely make snacks in the oven, specifically cheese stuffed pretzels. And on multiple occasions, my husband claims, out of some sort of pregnant woman rage, the handle would come off on our oven. It hasn't happened since, but during that snack-induced mania, I did get a good look at my oven handle, and indeed, it is a PET handle rather than a metal handle. The reason why you'd want something that's plastic as opposed to painted metal is it's the same color all the way through. If you scratch it, you're not going to scratch off the surface coating and see metal underneath. You're going to see the same color underneath. So it keeps that oven handle looking nice, and oven handles get a lot of abuse, like by pregnant women who desperately want their snacks. So now we are moving away from PET to other types of polyesters. This is PBT, polybutylene terephthalate. It is made by a polycondensation of terephthalic acid with butane-diol. So this is the same diacid, the same BB monomer, but what we have changed here is the AA monomer. This is a different dialcohol. It produces something that looks an awful lot like PET. The big difference is this particular segment here that comes from the butane-diol. So I will ask you this question: how do you make PBT? What are the starting materials? And make sure you pay attention to the fact that I'm asking for butane-diol. This is not a quasi-commodity thermoplastic. This is an engineering thermoplastic, meaning it has better properties, but it's also more expensive. And this is this is where we start to see some of our engineering thermoplastics starting to make their appearance. This has a different TG than PET. Because of the use of butane-diol instead of ethylene glycol, you have a more flexible chain. And what that does to the glass transition temperature is it lowers it. It lowers it a lot closer to room temperature. This makes it better for injection molding than PET. Its melting temperature is also a bit lower. This also rapidly crystallizes when cooling in the mold, which is better for injection molding, and makes for high injection speeds and shorter injection molding cycles. It has very good dimensional stability, it has good moisture resistance, but it does require drying for the same reasons that PET does, so desiccant drying at 121 Celsius for at least 4 hours. It has good electrical insulating properties. It has better resistance to hydrocarbon oils than PET, and better wear resistance and lubricity, otherwise it's slipperier than PET. It has, typically PBT is filled and fiberglass is one of the fillers. You can kind of see the effect of fillers here. So here is an unfilled PBT and here is a 30% fiberglass filled PBT. You more than double the tensile strength, you more than double the flexural modulus. You get better impact strength and you get much higher heat deflection temperature. So this is an example of what fillers do for polymer properties. The main application areas for PBT is in the fiberglass reinforced grade, and it has use in pump housings, gear wheels, automotive exteriors, electrical connectors, fuse cases, louvers, and high energy ignition components. Here are some encapsulation applications using PBT. You have an electro valve encapsulated with PBT polyester, and a Danfoss magnetic valve encapsulated with PBT polyester resin. So much like PET, it is a good resin for encapsulation. Now we are talking about yet a different polyester. This is polyethylene naphthalate, or PEN. This was introduced by BP Amoco in 1995. It has 200 to 500% better oxygen and carbon dioxide barrier properties than PET. It is stiffer, 50% stiffer, and has better heat stability than PET. It is much higher cost than PET. That is why it's not used for everything, and much less competitive at $5 a pound. It can be found in film, semi-crystalline and colorless, to crystal clear or slightly hazy, and also in granule form. This is often known under the brand names of Calidex or Calidar. The PEN monomers are supplied by BP Amoco, and these are dimethyl 2,6-naphthalene dicarboxylate, or NDC, or 2,6-naphthalene dicarboxylic acid, or NDA. NDA is an intermediate for NDC. This is how PEN is typically polymerized. This is your dimethyl ester. In this case, you are using the methyl ester portion. So this is reacted with ethylene glycol to produce polyethylene naphthalate. PEN has good chemical resistance to grease and oils, but very poor resistance to acids. It has good electrical properties, and it has good mechanical properties, and this is typically in a biaxially oriented film. Its heat deflection temperature is 155 degrees Celsius. PEN is competitive to PET. It's often used as a substitute for glass bottles. It's also used for ultra-thin data storage tape. It is used for refillable beer bottles. This is typically in the European Union. So these are bottles that are not recycled, but they are returned, washed, and refilled. They're used for high-performance tire cord, rescue ropes, UV-protected juice bottles, and sailcloth. There are many different polyesters, and depending on the monomers you use, you can make different polyesters. We talked about PET, PBT, and PEN, and then I have your composition. So this is terephthalic acid and ethylene glycol, terephthalic acid and butane-diol, NDC and ethylene glycol, but then we have some of these others. We have cyclohexane dimethanol, we have, and these are lesser polyesters of less commercial viability. But when you change out the monomer, you change out the properties. And so in this case, you have a polyester with better heat resistance than the other polyesters discussed above. In this case, you have a polyester. This is with 1,3-propane-diol, so somewhere in between ethylene glycol and butane-diol. Good dimensional stability, excellent surface properties. This is a copolyester with glass-like clarity and high stiffness. This is one with excellent clarity and better impact properties and better elongation than polycarbonate, which we'll discuss in the upcoming. And then this is higher heat deflection temperature and elongation, easier processing and drying, high clarity, and a neutral color. So when I talk about structure-property relationships, this is what I mean. You change your monomer, you change your attributes. And that has direct effect on properties of the finished part, but also your ability to process the material as well. So these are some of the biodegradable polyesters that we'll talk about from this point forward. And the one of most commercial importance at this point is polylactic acid. It is a thermoplastic aliphatic polyester. The other ones we talked about before have aromaticity in the chain. This is both biodegradable and derived from renewable resources. In the United States, the renewable resource is cornstarch. In Asia, this is either tapioca root, chips, or starch, and then in the rest of the world that is not Asia or the United States, it comes from sugarcane. So what you have here is, this is lactic acid. Lactic acid is also a byproduct of anaerobic metabolism. Lactic acid is what makes your muscles hurt if you've exercised to the point of exhaustion. But in this case, if you dehydrate it, so you take off a mole of water, you make this particular monomer, and then you can polymerize that monomer into polylactic acid. The resulting polymer has good biodegradation and hydrolytic degradation rates. Hydrolytic degradation is in the presence of water, biodegradation is in the presence of microbes. It has good film and packaging properties, it has good resistance to UV radiation, and it is relatively inexpensive, which makes commercial application a lot more likely. However, it has poor water vapor permeation, and that is where a lot of the work needs to be done. Another one is polycaprolactone. It has a low melting temperature, and it has a very, very low TG. However, this isn't typically used in the same applications as other things. It's typically used in the manufacture of specialty polyurethanes. And it gives good water, oil, and solvent and chlorine resistance to the polyurethane. It's often used as a resin additive to improve the processing characteristics and the end-use properties. Polycaprolactone can be mixed with starch to lower its cost and increase biodegradability. It can also be added as a polymer plasticizer to PVC. This is polycaprolactone. It is made from E-caprolactone. This is the monomer. You heat it up, this thing opens, and then this is actually an AB monomer. So here is your A. When you open this up, this has an OH group on it, and then this is your B. This becomes a carboxylic acid group, and then it can polymerize with itself. As a homopolymer, it has good biodegradation rates, it has good film properties, and it is inexpensive as it is commercially available. So people are looking at this more and more as a homopolymer to use as in place of other polymers for its biodegradable properties. Other ones are the PHAs. PHA stands for polyhydroxyalkanoates. These are made from bacterial fermentation of sugar or lipids. And this is a family of polyesters, so they can be all kinds of different structures. They are biodegradable and are used in the production of bioplastics. Depending on what your structure is, you can be thermoplastic or elastomeric with a TM ranging anywhere from 40 to 180 Celsius. It can be processed on conventional processing equipment. They tend to be UV stable with low permeation of water. There are more than 150 different PHA monomers that can be combined to give materials with extremely different properties. They differ in their properties according to their chemical composition, just like any other polymer we've talked about up to this point. You can have homopolymer, copolyester, and they can also contain hydroxy fatty acids, and hydroxy fatty acid is shown here. They can have crystallinity up to 70%. Their processability, impact strength, and flexibility improves with the higher percentage of valerate, and that is what is indicated here. This is valerate. They are soluble in halogenated solvents such as chloroform or dichloromethane, which also makes them good for fiber properties. This is one of the PHAs, PHB, polyhydroxybutyrate. It is very similar in its material properties to polypropylene. And it has, again, it comes from bacterial formation, so it comes from a non-crude oil source. It has a good resistance to moisture and aroma properties. Polyhydroxybutyric acid is synthesized from pure PHB, and this is relatively brittle and stiff. But if you create a PHB copolymer with other fatty acids like beta-hydroxyvalerate acid, you can create something that's a lot more flexible and can be up to something that's elastic. So you can tailor the properties somewhat from something that is from a bio-friendly source but has material properties similar to polypropylene. When it comes to the commercial degradable polyesters, PLA is the big one. The PHAs are also being developed as well, and won the Green Chemistry Award in 2005, and polycaprolactone is widely available. So this concludes the polyesters lecture, and we will move on from here. Thank you.